Hello everyone, in this particular lecture we are going to learn about VLSI Design Flow. What is the exact definition of it? What is its meaning? And we are also going to learn about its type, digital, analog and mixed signal VLSI design. So let's get started. I hope you have already seen the last lecture where we discussed about VLSI. What exactly is VLSI? So VLSI refers to the process of creating and implementing integrated circuits. If you want to know more about it, I'm going to link the video right here. You can go and watch it and then come back to this video. So these chips, they contain million or even billion of transistor on just one piece of silicon. Now, what is VLSI Design Flow? VLSI Design Flow is a structured path used to develop these very large-scale integration chips, and it includes everything from the initial idea of an IC to its final physical implementation and testing. So, what exactly is VLSI Design Flow? It is a systematic approach to create these chips, to create these modern chips, and it covers all the stages. Now, examples of these VLSI chips include obviously your smartphone SoC, your computer processor, your memory chips, and even your graphic processing units. You can even give me many more examples of VLSI. Now let's go on to the types of VLSI design flow. So we have digital VLSI design, we have analog VLSI design, and we have mixed signal VLSI design. Although we are going to focus a lot more on digital VLSI design, but we should also know about analog and we should also know about mixed signal VLSI design. The first one is digital VLSI design. What is it? The digital VLSI design, it involves creating circuit that process the binary data. What is binary data? 0 and 1. And what do we use to process the binary data? We use our logic gates and we use our registers. I hope this was very simple to understand because we have dealt a lot with binary data. We have dealt a lot with zeros and ones in our digital electronics, right? Now, the examples of digital VLSI design would be your microprocessor, your memory chips, your digital signal processors. Now, when we are designing these digital VLSI chips, there are some key steps. What are these key steps? First one is specification. What we are doing, we are defining the requirements for your speed, for your power, for your functionality, for your performance. Second one is your RTL design. What we are doing here, we are creating the design using hardware description language. What is hardware description language? I'm going to take another lecture on that in upcoming video. And for now, just understand that we have some hardware description language, for example, your Verilog or VHDL, where what do? We use those language to describe the data flow and to describe the logic of our chip. Next one is your verification. What we are going to do here, we are going to simulate the design to ensure that that chip is going to work as expected. Fourth one is your synthesis. What we do here is we convert our RTL design into a gate level representation. What we call it specifically, we call it gate level netlist. Fifth one is physical design. Here what do? We map the logical design to a physical silicon layout, including the placement, including the routing. Sixth one is your testing. What do here? We ensure that the design meets the timing and the performance criteria through various validation process. Now, the key steps are not just limited to these 6 steps. We have many more sub steps and we are going to explore the digital VLSI design in the next lecture. Make sure you do not miss it. Now let's look at the example of digital VLSI chip. Here is our microprocessor Intel Core i7, and what does it have? It has millions of transistors which performs the calculation, which does all the tasks it's intended to do. Now let's move on to the second one. The second one is our analog VLSI design. Whenever we hear the word analog, what is the first thing that comes up in our mind? Signals, right? So analog VLSI design, it focuses on circuits that produce continuous signal. For example, your audio signal or your voltage levels. And it is essential for application which requires a precise signal manipulation. For example, your amplifier, for example, your oscillators, for example, your analog to digital converters. Now, when we are designing any type of VLSI chip, there are many steps which are absolutely common. For example, obviously you're going to have a specification, right? When you're designing a chip, obviously you're going to have specification. Obviously you're going to make a block diagram. Obviously a team will come up with the architecture. But what are the additional steps which are included while we are designing our analog VLSI chip? First one is our transistor level design. Here we are emphasizing, we are giving the extra emphasis in designing at the transistor level to achieve the desired signal characteristics, because here the processing of signals is very important to us. Second is our analog simulation. We use specialized tools, for example your spice, and why we are using it? To simulate the continuous signal to ensure that we have a proper performance from the chip. One more step which we can look at is your custom layout. See, here we are placing our components very carefully. Why we place them very carefully? Because we want to minimize the noise and we want to ensure the signal integrity. So this is the place where we are going to emphasize more. Now let me show you an example of this. See, this is an analog to digital converter chip. The name is Maxim ICL 7107. What is it? It is a monolithic ADC chip. I hope you know what is ADC. Please write in the comment section what is the ADC. Yes. So these have very high input impedance and they don't even require any external display. Here we have a lot more onboard active component. For example, it would have segment decoders, it could have clock circuit, etc, etc. Now let's move on to our last type, which is mixed signal VLSI design. It's quite popular nowadays. I hope you have heard of this term. So here we integrate both digital and analog circuits within a single chip. And what we are doing, we are allowing for more versatile application. Because in some chips, what do we need? We need that my chip must be able to handle both type of signal. It should be able to handle an analog signal as well as a digital signal. For example, your system on chip. For example, your RF receiver. For example, your image sensors. Now, what are the additional steps which we take apart from the common ones? What are the areas where we emphasize more while designing a mixed signal VLSI chip? First is your mixed signal simulation. We are simulating both analog and digital sections together. Why we are doing it? We are doing it to ensure smooth interaction and seamless operation. Second would be your layout consideration. See, we are carefully integrating the digital and analog components. Why we are doing it? To prevent interference. Third one would be verification techniques. We are combining timing analysis for digital logic and signal integrity checks for the analog components to make sure that the overall performance is good and it is working as intended. Now I'm going to show you a very popular example and a very famous SoC, which is your Qualcomm Snapdragon 888. I hope you know about phones like Samsung Galaxy S21, your Vivo X60 Pro, your Xiaomi Redmi, Oppo. Many phones in the year, roughly I would say 2021, most of the phones had this chip. Why this chip is very special? This combines the digital processing capabilities, the CPU, GPU, with the analog components. I hope you understood all the three types. What is the digital VLSI chip doing? It is handling the digital signal. What is the analog VLSI chip doing? It is handling the analog signals. And what is a mixed signal VLSI chip doing? It is handling both of the signals, right? In the next lecture, we are going to learn a lot more about digital VLSI design process. We are going to understand the entire development cycle. So make sure you watch that. It's an important one. Till then, bye.